Well, hello everyone, and welcome to the November 2021 edition of the St. Louis Java Users Group. For those who don't know, the St. Louis Java Users Group is a pretty informal group. Attendance is free. We don't maintain a formal membership list or anything like that. Our normal meeting date is the second Thursday of every month, except December, when there is no meeting. There's just too many things going on over the holidays for us to be able to organize a meeting then. Due to the pandemic, we have been meeting online, but when we meet in person, we have people join us for food and social at 6 p.m. and the actual presentation starts at around 6:30 p.m. When we do meet in person, our normal meeting location is in the Object Computing Incorporated training room at 12,140 Woodcrest Executive Drive, and that's Suite 310 upstairs. And of course, that is in St. Louis. I'd like to introduce the other members of the steering committee. So from left to right, we have Ted Doyle, Todd Zimmerman, Bruce Allspaw, that's me in the middle, Wei-Chi Gao, and Kathy Zwang. You can reach all of us on the steering committee if you just send an email to that address there at the bottom of the slide. That's javasigsc@ociweb.com. The St. Louis Java Users Group would not be possible without the support of our sponsors. So I threw up a few logos here for some of our sponsors. I'd like to thank Object Computing Incorporated. They are our founding sponsor. They've been with us since the group was formed back in, 1997. That was before I was ever on the steering committee, long before. And they have, of course, sponsored the room. And they also sponsor to fill in whenever we just have gaps to just make the meeting possible. J Frog has been a fantastic sponsor. They have been sponsoring the meetup fees and the Zoom subscription, and also on occasion they will come online and they will have a raffle for a prize as well. When we meet in person, we like to have food and pizza, and Signature Consultants as well as Adaptive Solutions Group have been great when it comes to sponsoring the food. They are headhunters. So if you are looking for a position, they would be a great companies, both of them, to talk to. You can just look them up online, just with a quick Google search, and let them know that you found out about us through the St. Louis Java Users Group. And the same also goes if you need to hire a developer. They can see if they can help you to find somebody. At the end of the presentation, we will be raffling 2 JetBrains licenses, courtesy of JetBrains, so that's why their logo is there. When we meet in person, we also have some gift cards that have been sponsored by Elastic. We haven't figured out a way to send those out over the internet, so we're just going to hold on to them, and they're still good until we can actually start meeting again in person. Also, Intertech has been a good sponsor as well. They sponsor the famous Screaming Flying Monkeys. What in the world are those? They are little dolls, and if you throw them up against the wall, they scream, and they are just so much fun. And usually they'll throw in some coffee cups and mouse pads too. Intertech, I should mention, is a training company. And if you look them up, you can find a lot of online training, so that if you're looking to improve your Java skills or just your software development skills in general, Intertech would be a good place to go. We will also be raffling 2 Manning ebooks. So that's why their logo is up here at the end of the meeting. But I should also point out that in order to win these JetBrains licenses and Manning ebooks, you must be present to win. Sorry if you're watching the recording, it's too late. You do have to actually be here. And we also have a sponsor, Pearson, which will on occasion sponsor physical computer books as well. So thank you for all of our sponsors. I do have a couple of announcements here. The No Fluff Just Stuff conference is going to be coming here next spring, and as far as I know, it's still on. That will be April 1st and 2nd, starting at 7:30 a.m. at the St. Louis Marriott West in St. Louis. There should be options for people to attend both in person and online. And if you want to get more details about that, just go to that address there at the bottom of the slide, nofluffjuststuff.com/St. Louis. Now, there's been a change here on this one on our meeting announcements. Before, I was advertising that the jconf.dev Java conference was going to be in Chicago, and it had an option for in-person and online. Well, guess what? That's changed. Now, jconf.dev is going to be one day, and it will be entirely online. And guess what? Registration is now free. Kind of hard to argue with that price. So if you're disappointed that we're not having a December meeting, well, now you've got a great place to go here on December 9th. Just go to that address there at the bottom of the slide, 2021.jconf.dev, and you can attend lots of presentations there at JConf, and who knows, maybe I'll steal some speakers out of that one. Anyway, so I just wanted to get that word out here. So as far as upcoming presentations go, as I mentioned before, there's no meeting in December due to the holidays. We almost never have one. But mark your calendars for January 13th, because we've got a great presentation. Your internal developer platform is suboptimal, by Alan Barr of Veterans United Home Loans. And I've seen his presentation, and it's actually pretty good on how they've developed an internal development platform for their organization. Veterans United Home Loans is actually headquartered in Columbia, Missouri, where I happen to be. And I happen to know some of these folks here. So it works great, actually, regardless of your, whether it's Java or maybe, dare I say, .NET developer. Anyway, I'm looking forward here to that one. So as far as upcoming presentations go, if you want to keep up with our presentation schedule, the easiest way to do it is just go to our webpage there on Meetup. It's just meetup.com/gatewayjug, and you can get the latest updates to the presentation schedule and location as presentations are scheduled. We just put them on the Meetup page, and you can RSVP for them as soon as they show up. Now, if you would like to give a presentation, or if you're interested in sponsoring the Jug, just send us an email to that email address that I mentioned before. That's javasigsc@ociweb.com. So those are my announcements here for tonight. Our speaker tonight is Mike Yawn of Hazelcast, and he's giving a presentation here on event streaming. It's not just for events anymore. So what I'm going to do here is I'm going to click this stop share button, and that should enable Mike here to share his screen and take it away, Mike.
All right, thank you. Let's see, I guess I'll share the desktop because I will switch over to the IDE at some point. So as Bruce said, I'm Mike Yawn. I'm a senior solutions architect at Hazelcast. Since this is a Java users group, I'm going to talk a little bit about my Java credentials. I've been working with Java since the 1.0 release. At the time that came out, I was working in an R&D lab at Hewlett-Packard, and part of my job was actually to recruit third-party software vendors and to help port them to our proprietary OS platform, which, as you might imagine, was time-consuming and expensive to do. So one of the engineers at one of the vendors that I was working with, who was talking to me about, they were thinking about rewriting their app in Java so they wouldn't have to keep porting it to all these different platforms. And I just kind of thought, well, that could really work to our advantage, because then we wouldn't have to spend so much time and effort recruiting people to run on our platform. So I just started really as a spare time project, before there was official management buy-in, porting the JVM to our platform, and did that kind of as a spare time project initially, released it as freeware, and then it eventually did become a supported product from HP. And then after that porting work was done, I went on to do Java performance work at HP. After I left there, I did developer tools at eBay, worked on the Java debugger at Oracle. And now I'm kind of going back to my, my oldest roots of like starting out as a software engineer, working as a solution architect with Hazelcast, which has me focusing on high performance, low latency software designs based on in-memory technology. So, it's been a long way since Java 1.0. So the agenda tonight, I'm just going to do a brief introduction to Hazelcast, who we are and what the products are that we have. And since we started out as an in-memory storage engine, primarily for caching, I'll talk a little bit about that. But then the bulk of the presentation is about stream processing and how you can use stream processing to solve performance bottlenecks and application workloads that you might not actually describe as or think of as being stream processing applications. And I've tried to make this generic because, a lot of times users groups like you guys don't want people coming in doing a product pitch per se. So where possible, I try to make it generic, but some of the features I talk about are kind of unique to our product. So I'll just to kind of mitigate that, I'll say everything I'm talking about tonight are features of our open source product. So if you like it, you can go out, you can, grab the binary, you can, fork the repo on GitHub, build it yourself. I am not talking about any enterprise or, pay for features tonight. So this is all stuff you can do with open source software. So this is our platform architecture. We have, if you look at this, we've got the Hazelcast platform here in the center, and then kind of around the edges, we see the things that make up the ecosystem that we operate in, the different clients, connectors, databases we talk to, that kind of stuff. And the platform is divided into two components. And if you have any historical association with Hazelcast or are familiar with us, this might be new because this platform is just something we released in the past year. We previously had two products that were separate, or if you're using the open source, separately downloadable modules that we've now merged together. So the older one, this is about 12 years old, is our in-memory data store. This was called Hazelcast IMDG. It is essentially like a key value store or caching solution that you can put in front of a database, pull all your data into memory so that you have very fast access to it. So that's the in-memory data grid. On top of that, we've got our newer product or piece of the platform called, when it was a standalone product, we called this Hazelcast Jet. We still use that term, even though officially they're trying to, scrub it out of a lot of the documentation, but you kind of got to have a name to call it by. So we still call it Jet, but it is, officially the stream and batch processing engine within the Hazelcast platform. And so that is really the focus that we'll be talking about tonight. And this is a way of providing distributed computation with high throughput and low latency. And we'll see how we achieve that as we go through the presentation. On the edges, left and right, we show that into our computational engine, we have connectors to all sorts of data sources like Kafka, JMS or MQ, sockets, files, application connectors. So just, anything that might be a logical source of data, we probably already have a connector for. And if not, then there's a SPI, so you can kind of write your own custom connectors. And then so data flows in from these connectors into the stream processing engine, goes through compute. We can enrich those events that are coming through with reference data or historical data or contextual data from the in-memory data store. And then when things are finished, we can publish that out again through various output syncs, which again could be Kafka or MQ, write it into a database, publish onto an alerting system of some sort, a Grafana dashboard, whatever's appropriate. At the top of the diagram, we show that there's various clients that we can use to connect to the platform in various languages, including Java, C#, C++, Node.js, Python, Go's. Oh, actually, Go is shown on here. We now have a Jdbc client. This is fairly new. We also have support for SQL from all of these languages, which is fairly new. So a lot of different ways to get data in and out of the platform. And then down at the bottom, finally, we show that we've got various systems of record that we can talk to, that this is your persistent data storage. And we have various interfaces to load and store to these systems of records. So that's kind of the platform in a nutshell. And I should say, please, especially because we don't have a huge number of people, so that we can definitely make this interactive. If you see questions as we're going through, just feel free to jump right in with them.
Small question then, real quick.
Yeah.
Yeah, right there. Thank you. For the platform, would you call this like an enterprise service bus a little bit more, with a good hosting of records that you have permanent storage for something that you're streaming through the system? Because it has a really good flavor of it, and I like it.
We definitely think that is a use case that we can fit into. And I think in some ways, this is just playing with the semantics, that the terminology we use more is digital integration hub. So, and part of that is we don't actually have all of the, say, resilience features that, say, Kafka has. So we see people using Kafka more for the data motion through the system. What we can then kind of do is give you this common data layer that connects to a bunch of different backend systems. So you may have, MySQL and Mongo and Cassandra and maybe DB2 on a mainframe, and all these places that, have data that is useful for processing this data. So, Kafka kind of becomes the messaging platform through it all. We become the compute and caching piece of it. And then for the most part, the databases, the persistent data tends to stay where it is. We've recently been adding some persistence capabilities, but I'm not sure that I would yet say that we fall into the role of, being a replacement for your traditional relational or NoSQL databases. But as we add more persistence features, that
one
may
of the things that you have on your slide is the actionable context. And could you expound on that a little? Because it's like, all right, we get all the pipes in, we're combining, we're streaming. So you're not like enriching or anything, but where is the fun stuff in that space?
Well, I mean, we do enrich. We do, as data comes in, it's very common that we would enrich that. So for example, one of the use cases that we have for the platform is several very large banks use us for fraud detection. So you've got a credit card swipe coming in from a point of sale terminal somewhere. But in order to determine whether that is potentially fraudulent or not, there needs to be a lot of contextual information about previous transactions on that account, about data about the merchant, perhaps what their average sales amount is. There might be geolocation info that might be coming. If you've got one of that bank's mobile apps, they might actually be looking and seeing if you're at the same location that your phone is at. And if not, that might be a reason to be suspicious of that transaction. If you're swiping a credit card apparently in St. Louis, but your phone is in New York, it's like, maybe that's not really you. So that kind of contextual information is combined, with the transaction coming through. And then frequently we may pump this out to a machine learning inference engine to do further calculations on that, because we can really kind of help productionalize those machine learning applications. We don't train the models. We're not in that end of the business. But once your data scientists have created the model and you say, okay, now I need to execute this at scale, because the platforms like Flask or something that maybe your data scientists use, it's like, well, this can only do like 20 operations per second, and I need to be doing tens of thousands of operations per second. So being able to scale that up is kind of the place that we play.
So what kind of throughput do you think that you could achieve? Because I'll give you a small use case that I saw at a large credit card company. We will leave them nameless here, but they were actually selling something called advice. And they were actually having to have all of their transactions for advice to actually resolve in 0.8 seconds. That was the SLA for every piece of advice that they were selling to their card members. And so do you think that your system could achieve that type of throughput for those types of rules that you just stated to achieve that?
Yes. Yeah. We I think I've got the slide in here later. Again, this wasn't an ML case, but there was like a benchmark where we did 1 billion transactions per second.
Nice.
And on those, the latency was under 30 milliseconds. And that was in an AWS cluster of 45 nodes. So yeah, I think definitely we can scale up. Most of our, like the fraud detection use cases, I think typically they have SLAs in the neighborhood of like 20 milliseconds, which they prefer to see our slice of that be maybe in single digit milliseconds, because they've got other things to do besides the piece that's running in our engine. So yeah, I think that's a reasonable target that we could meet.
I've got a question here in chat from Sean. He's asking, I've heard of reactive. Is this related to reactive streams at all?
It's, and I am not that familiar with reactive, so I would just say, based on the tiny bit that I know, I feel like that's a no, but somebody who knows better might say something different. But I'll just say that's not the terms that I've used to describe it, when we go around and talk about the product. So let's move on, but definitely keep the questions coming as you come through, as you come up with them. So again, before we jump into the stream processing, I just wanted to talk a little bit about the in-memory storage piece of the platform, which is where we started out. And the way I like to talk about this is to kind of go back. Like I say, I started with Java 1.0, so I've lived all this history. And probably the most used data structure within Hazelcast is our implementation of a map. And our map, which we call an IMAP, is really just the next logical step in how maps have evolved in Java. So if you go back to Java 1.0, we had the hash table. And if you know hash tables, all the methods on a hash table were synchronized, which meant that you got thread safety out of the box without having to think about it, but it doesn't really scale well for multi-threaded applications. So in Java 1.2 or the Java 2 release, they completely flipped that around with hash map, which had no automatic locking in it. Kind of essentially said, we're going to make you, the application developer, responsible for locking and synchronization. So I suspect this probably resulted in a lot of fast, unsafe code. So then in Java 1.5, this was like a real breakthrough. They came up with the concurrent hash map, which was the first safe and scalable implementation of the map interface. And the secret sauce here, if you will, concurrent hash map is a segmented data structure. So rather than locking the entire map, when you need a lock, you just lock the segment that you're going to do an insert or an update to, rather than the entire data structure. And by default, a concurrent hash map had 32 segments, meaning you could have 32 threads updating that map concurrently. So that's a huge move forward in concurrency. And so the Hazelcast founders freely admit, it's like, hey, we just took that idea and said, let's run with that and go a little bit further and say we could actually scale this out even more by allowing these segments to be placed on different servers so that we can go much larger than the memory of a single JVM. So that's essentially what an IMAP is. Now, I don't mean to trivialize how hard that is, because adding in all the complexity of networking and partition management when you can have arbitrary delays and things can go down, that's not an easy thing to do at all. But conceptually, it's really easy to say, oh, you just took concurrent hash map and scaled it out horizontally across a bunch of different nodes. And that's what an IMAP is. In addition to the clustering, another key value that Hazelcast adds there is that we instituted a threading model where all the partitions, which is what Hazelcast calls segments, get a dedicated thread called a partition thread, and only the partition thread is allowed to read or write a particular partition. And because of that, you almost never need to lock things in Hazelcast, because all the requests, reads and writes for a specific partition will get queued up for the partition thread, and it will execute them in order. So things just kind of are linearizable for free without any need for locking. And we get really fast access at high levels of concurrency. And then the partition thread count, it's something you can tune, but by default, we just set it based on the number of processor cores. I think we go by twice the processor cores. So if you've got like a 6-core system, we'll have 12 partition threads because they're not all going to be active at the same time. I think that's all I was going to say on that one. So I just pulled a couple of slides here out of a sequence talking about different things. The APIs that we have, a large part of the APIs are essentially just taking the Java collections that you may be familiar with and doing distributed implementations of those. So again, map is the most popular, but we have set, list, and queue as well, along with other APIs as shown here in the green. But just having all of those things that as a Java programmer, you already know how to use, and saying, hey, we'll give you distributed versions of these that you can use to really scale up to massive applications is a lot better than having to learn an entire new way of doing things. And again, just to kind of say how those collections are used, caching is one of our most common use cases. And because it's our most common use case, there's a lot of features built into IMAP that go beyond just a map or concurrent hash map. So for example, map loader and map store, these are your interfaces into a persistent database, so that, for example, if there's a cache miss and you have a map loader associated with the map, then we'll ask the map loader to like go fetch that key from the database, and then it'll insert it into the cache before returning it to the user. Similarly, if you update something in the cache and there's a map store associated with that map, then we can use the map store to do either a write through or write behind to update your system of record. And then we have things like TTL, eviction, change data capture so that you stay in sync with the underlying database. We are kind of plug-in compatible with JCache and Hibernate second level cache, and integrate real well with Spring. Not sure if he still is, but at least initially, Rod Johnson of Spring was on our board of directors. So we kind of go back, to the very beginning of the company with his assistance. So now let's get into the meat of what I, said I wanted to talk about tonight, which is, the stream processing use cases. And let's talk about two different scenarios. In the first case, I have a stream of events coming in and I need to process them, efficiently, minimal delay. And so that sounds like a stream processing use case. So if you have a stream processing engine, then clearly it makes sense to use that. And that's actually not the use case I wanted to talk about tonight. The use case I wanted to talk about was much broader, and just say, you've got software that your users or your manager or whoever, or you yourself are just saying, why can't this go faster? It's just, it's a bottleneck. And so that may or may not be a good use case for a stream processing solution. So let's drill down on that. What sort of things can a stream processing solution make faster? Just being a smart ass for a bit, it has to be software. We're not going to make your DMV visit shorter or get you through traffic faster. But if it is software and it's taking too long, then, let's keep going. Generally speaking, it needs to be something that is repetitive, software that contains a loop. If it's just one big massive thing, that's probably not a good candidate. It also should be a loop that's made up of multiple steps. And the reason for that is because, as we're going to see, what Jet is really good at is helping you do things concurrently. So if you're just doing one step, it's hard to get concurrency out of that. But if you're doing, 8 or 10 steps, then we might be able to say, let's look at getting concurrency between these different steps. And then the kinds of steps within the loop. Now, I will say that we can essentially, almost anything that can be written in software could be part of a Jet pipeline. But the things that we're kind of optimized for are, fetching data, processing it, sending and storing the results somewhere. Actually, those were the very broad ones. Here, this was the slide where we drill down into what are the things, when we say processing, what do we mean? Filtering data, just doing a simple, you've got thousands of items coming in, say you're an IoT application where data's coming in from sensors, and maybe you just don't care about data that's within normal bands. It's like, okay, temperature in expected range, we're just throwing that data away. We don't need to do anything with it. But if it's out of band, then we want to continue processing. We're going to need to alert on this. Transforming data. This is one of the really powerful things that we can do in a stream processing engine. Enrichment, and this came up in like one of the questions. you know, if we have data coming in, again, that sensor data, those tend to be really sparse pieces of data. You know, a temperature sensor, it could be that all it sends you is a temperature. And it's like, well, you don't know if that temperature is good or not if you don't know where the sensor is located and what the expected range is for that. And that's probably not all in the data that's coming in. So you actually have to have some contextual data to help you evaluate the data that's coming in. My slide stopped advancing. Let me get back. There we go. Aggregation, this is another really common thing to do in a stream processing framework, is that you have these individual items coming in and you may do a lot of processing on them individually, but you may also want to aggregate them on some key and just, you know, get those totals for, you know, publishing to a front end graphical system or passing downstream for further processing. So, you know, grouping items together based on some field value and aggregating them is one of the things that we can do real well. Sometimes also these aggregations are happening within timing windows, which is, again, really common and easy to do with the stream processing framework, but difficult to do in other situations. So a lot of Jet functionality is around timestamps, handling out of order events, windowed aggregations, those sorts of capabilities. So, you know, code is worth 1,000 bullet points on slides. So just to kind of give an illustration of this, here's a simple loop that's doing some fairly simple processing. And if we look at this, conveniently, if we add up all these steps, it takes about 30 milliseconds to go through and process one item here. So that means we can do about 33 items per second. That's not bad. And then we'll just have to do that for however many items we have. So if we've got 1,000 items, then this just takes us 30 seconds. But if we've got 1,000,000 items, then it's going to take us 30,000 seconds or a little more than 8 hours. So that may not be acceptable. So if we need to improve concurrency within this loop, then that allows us to reduce the time dramatically. So how do we get to there? And there's essentially two different approaches that I'm going to talk about. One is we can reduce the amount of time that you do that it takes to execute these individual steps. And then the second approach is, again, the main focus here is about concurrency, which is we can be doing a lot of these things at once. And with concurrency, we also have two different ways that we can approach concurrency. Oh, actually, I did want to make one point back on this slide, which is, you know, reducing the amount of time required for individual steps. It's not really the focus about talking tonight, but it's one of the things that the in-memory data grid part of Hazelcast does really well, because if you've got the data cached rather than having to go out to a database for it, then that can, you know, shave off seconds of time. And then the other thing between these two different approaches is reducing the amount of time that individual steps take is always going to be a win. I mean, there's no case I can think of where that doesn't make your application faster. Introducing concurrency really only helps you if you've got extra computing capacity to allow you to be doing that. So if you're completely maxed out on CPU, you know, this doesn't help. But on the other hand, if you're on an 8-core system and only 2 cores are busy, then this is going to help a lot. So introducing concurrency, we will look at 2 approaches here. One is to partition the input, and then the other one is to execute those individual loop operations in parallel fashion. which, in Jet terminology is pipelining. So here's an example. We've got an input source here with 6 items, and we've got a single processor. And so we're just going to process these one at a time. And obviously it's going to take us, 6 units of time to get through our input. Whereas if we partition the input across 3 different processors, then each processor, can take 2 of the items, and essentially in 2 time units, we will have processed all of them. This is, not rocket science. I'm probably not telling you anything you didn't already know. And this is also usually fairly straightforward to implement. So the more interesting case here is pipelining. Let's look at application code that does not use pipelining. And this is kind of a bit more blown out example of the simple example I showed earlier, which in this case, we're going to loop for as long as we have data and read transactions, in this case, coming in from Kafka. We're going to do the use case here. This is actually something that we are working with the customer to implement this for reals, is based on, when you use your credit card at various places, a lot of times they will, tell you to opt in to various different deals. And it's like, oh, if you use your credit card at a gas station, you get an additional some % off, or if you, go to this particular merchant, then something. So we're kind of like, this is a more real-time version of that, where, as the transaction comes in, if you've opted in to receive these offers, then, we load your account info. This is that enrichment that we don't know the account info. All we've got coming in is an account number. We'll pull in your recent transactions, and then we will run out to an AI model to kind of like crank through, depending on the recent transactions you've had. We're going to pick a top 3 offers to show you on your phone, right now, not like, hey, this will be on your statement at the end of the month, but actually give you some real-time offers that you can accept right at the point of purchase, essentially, and send that off. In this case, we're writing back out to Kafka, where it'll get routed back to a customer's mobile device. So all of this is happening on a single thread. So none of these things are happening concurrently. Now, we could take this same thing and make every one of those different operations independent and a separately executable tasklet. And then they all kind of run concurrently. And this, the analogy that works for me is if you think of a bucket brigade, where you're just kind of like handing this bucket down, a line of people. Every person is just doing a tiny bit of work, but they're all staying busy. So, the way that a Jet pipeline for this would look is, we read in again from Kafka, we filter out the ones that aren't opted in, we pull in account info based on the account key that's in the Kafka transaction. We also pull in recent transactions, and then we invoke our service factory here, passing it the data that we've enriched, and get back a series of offers. So again, the code looks very similar. From a developer point of view, this is not really any harder to write, might even be a little bit easier. And one of the things that you'll notice here is like, we are not doing any flow control here. This is all declarative. We're just saying, these are the steps. We're not writing the loop. We're not saying how many of these things should you be reading? Should you be reading in batches? Should you be reading individually? How are you passing these items around? None of that is on the developer. You just kind of say, I want you to do these steps, and I want you to figure out, how to best lay them out. So from an implementation point of view, what's happening is that each one of these steps is a separate tasklet. And then the tasklets are separated by queues because they're not all going to operate at exactly the same speed. So, you know, we read from our source, and as we read things out, we publish these to a queue. And then we have a filter tasklet that reads from the queue and, you know, does not, you know, some items it's going to be throwing away, but the ones that pass the filter, it writes out to the next queue, and so on down the line. Now, what's interesting here, and I didn't draw it because it would just get very busy, each one of these steps can be replicated. So there isn't just one read from, or depending on the source, if the input source isn't partitioned, there probably is one read from. But we might then round robin write these out to 4 different queues, for example. So now we've got a parallelism of 4 going through the next stage of the pipeline. And then the filter will write them out, you know, probably still 4. The enrich, that might take a while because we might be waiting on a database to like get back to us. So we might have a higher degree of concurrency here. Maybe there's 8 of these guys running. And again, none of this is things that you need to configure. These are things that Jet figures out by seeing how full the queues are getting. You know, if a queue gets full, back pressure is going to, you know, block things upstream where they won't be able to write anymore. And at some point, that's going to cause certain of these things to start getting scheduled onto more processing cores to kind of help, you know, break that log jam and get data flowing through more quickly. So all of this optimization kind of happens, you know, apparently by magic, but really just through simple flow control algorithms, seeing how full the queues are and adjusting the number of tasklets of each type running accordingly. It's also worth mentioning that, and I think this is true of all stream processing engines, so I'm not sure there's anything unique or different here, but you know, when I describe the pipeline, you might be picturing it as just, you know, the same data item that you read from the source running through the entire thing. And in reality, it's probably something different at every stage. You know, when we read in a map entry, oh, well, filter isn't going to change that. That's still going to be a map entry. But when we enrich it, now suddenly we've got the transaction and we've got account info. So our data structure from here is different. And then when we pull in recent transactions, now we're passing, you know, a transaction ID or account ID, I think was the key here, and then a list of transactions. So the data gets transformed potentially at every step during the pipeline. And just to make things more complicated, we can actually use those 2 approaches together, partitioning and pipelining. These are not mutually exclusive. So what we've got here is showing in the first case without partitioning or pipelining, if we just had a simple step that took 5 time units, then every time unit, 5 time units, we'd complete 1 item. So in 15 time units, we would finish 3 items. If we did just partitioning, we would essentially say, okay, I'm going to have this process running on 2 cores. Each one of them can do 3 items in those 15 time units. So now my total throughput is 6. But if I do, if I do just pipelining, so not partitioning in this case, then in time unit 1, you know, I read this first item. Then in the second time unit, I pass this first item along to the next task while reading the next entry. And then in the next time unit, you know, this moves along to the third task, this moves along to the second task, and I read the third unit. So you can kind of see how that, you know, all cascades along in a 6-core system. After 15 time units, I've actually got 13 units completed. and 4 of them are still in flight here. They haven't completely completed working through the pipeline. And then if I do partitioning and pipelining together, I just thought that was going to be too complicated to draw. But essentially, again, if my, partitioning into 2 units or reading 2 units in every cycle, essentially, then I'll get through, again, twice as many as with just the pipelining. Or just the partitioning, I should say. So one of the examples, that was kind of an example that I had worked through because I was doing something similar from one of our banking customers. This kind of goes back to the very beginning of Jet, and I would actually say, far predates Jet. If you go back to like Hadoop and MapReduce and Spark and Flink, I mean, all stream processing engines use word count as kind of an example because it's like the hello world of stream processing. So if you wanted to count the words in a document and say how many times does, say, the word of appear or the word the appear, then essentially you just read in a line at a time, you tokenize the line into individual words, and then you update, running counts of each one of those. So, here's a simple implementation of that where you essentially just read lines of text, split them using this pattern, and then for each word, update counts. And you just do that till you've processed all the words in the document. So let's look at how this maps onto a stream processing solution. So we've got a source where we read the text from. We're using these queues to separate out the steps. So instead of this just being single threaded, we essentially can think of logically having 4 different processes here. We've got our reader process that outputs text. We have our tokenizer process that reads text and outputs words. We have an aggregator that reads words and updates a map saying for that word, the count is now this. And then we publish all that to somewhere, into an IMAP in the Hazelcast case. So that essentially is how we, went from a single threaded to now we have 4 different processes all running together. Again, the bucket brigade kind of analogy. But we can do even better by saying, okay, we can split some of these. We could have 2 tokenizers. Our source could just kind of round robin, fire one line off to one, then another line off to the next. And that speeds up this task. It doesn't help us anywhere else in the pipeline. But if this had been our bottleneck, then, we've just helped alleviate that bottleneck. But we can also split this one out. So we can do 2 of the aggregators. And now we have to have a little bit more intelligence here that as we tokenize, we have to know, will these words go to this aggregator, these other words go to this other aggregator. We can just do that with a simple hashing function, which is how Hazelcast puts things into maps anyway. So we kind of have this, built-in functionality to help us route things to the proper place. And then we can take essentially this entire thing and replicate it across multiple nodes. And here we've added an additional step after the accumulator because we're going to say, well, our accumulators, we don't want to pass too much stuff back and forth across the network. So an accumulator is just going to be for a single node. But then when we finish the accumulation, then we'll combine all those results across nodes to get our final result. So this is the word count example implemented as a Jet pipeline. So it doesn't, again, it's not really more complicated to do than the single threaded version we saw to begin with. And just so that we have something in here that's more than just PowerPoint, I've got this demo loaded up. I will fire up the Jet pipeline. Now, the longest part of this, the pipeline itself runs very, very quickly, but I started off without anything running. So it actually is going to launch Jet in an embedded fashion and load up the DAG and then run through everything. And so there the job is finished. If we kind of go back and look at what happened here. So we started up an instance of Hazelcast Jet, just a single node running on my laptop. So right here, we get that it's started. We read in the complete works of William Shakespeare from disk, and then we run through our word count. So we see that the job was started. This is kind of a reliability feature. If we had an interrupted job, it would have resumed the interrupted job, but there wasn't a snapshot. So we just said, okay, we'll run it from scratch. It looks at this code up here that we've essentially defined in a pipeline, figures out the optimized DAG for executing that, and then runs through, gets the execution plan, starts it, runs through. Our total elapsed time here was 1.25 seconds to read through the complete works of William Shakespeare and count the words. So guess this is counting the job launch time as well. And then as a validation, we just know, hopefully somebody didn't count these manually. We know how many times the word "the" occurs. It is the most common word, appearing 27,843 times in the complete works of William Shakespeare. And we could have outputted the entire thing here, but we just put out the top 100 entries. And once we wrote the result, then we shut everything down and that job's completed. So jumping back to slides. Just to show, because this is a really common use case for stream processing engines, we can run word count and compare it to other platforms. So for example, we can see this is batch processing, so it's throughput. So for throughput, higher is better. So the highest is Jet. When we have actually pre-ingested the data, we read it into an IMAP and then process it at in-memory speed. But even if we don't give ourselves that advantage, even if we say, well, we're going to read it in from disk, we're still considerably faster than Spark or Flink doing the same workload. And then we can also do this as a, so this is essentially measuring throughput. We can also look and say, well, what about latency? For latency, you obviously want numbers to be smaller. So from, the time that a word or, from a line being read until we get all the output of the entries on that line, again, we see running considerably faster than either Flink or Spark. So I thought I had the million operations per second benchmark in here. I guess I do not have, or excuse me, the billion operations per second one, but I guess I did not load that one in. So that was essentially what I had for tonight. I'm going to share these slides with Bruce afterwards. I think he'll, I think you guys have a website or something to put these up on, so you don't have to scramble to write all these URLs down. But yeah, just introduction to the platform, showing specifically use cases about streaming and batch, and then just my own shameless plug. One of the things I do for Hazelcast is this web series that we call Hazel Vision. We've got the first 5 episodes up. I've actually recorded 9, so there's a few more to pop up. And when they do pop up, you'll see episodes 7 and 8 are going to look really familiar, because that was kind of the starting point that I used to put together tonight's presentation. But tonight's was considerably extended because the goal on these is to try to keep them around 5 minutes each. So we just want them to be, a quick hit, go in, learn something. And then if it's interesting, give you links of where to go find more information. So questions on that? I will stop sharing so the next person up can.
Peter, you generally have a lot of questions.
What was your biggest concern of trying to get that billion records per second accomplished? Because speed in my life has always been earned. It's not quite given freely. I'd like to know what challenges you faced.
And we had something that partitioned very cleanly, I think is a lot of what helped there. And I can't think of a good example right offhand of things that don't partition as cleanly. But if all the things that you're doing are completely independent, then you can essentially scale up linearly with almost no knee of the curve. You can just add in more processors and keep going. Where things become more challenging, and again, this was an industry standard benchmark, and I'm not even exactly sure what it's doing, but in real world where we sometimes run into things is, let's say you're a retailer and you've got 10,000 items that you're selling. You're not going to sell equal quantities of all 10,000 of those. When you go on to have a sale or something, Black Friday, there's certain, your doorbusters or whatever that are going to be the points of contention. And that's always where it seems like the challenges come around, is like if everything spreads out really evenly, it's not that interesting. It's just the fact that we can take advantage of all the processor cores, that everything is in memory. It essentially just says, as long as we keep throwing more hardware at this, it will continue to get faster. But when you've got those bottlenecks of, everyone is trying to access the inventory record for the iPhone 13, that is where we're backed up, as everybody's trying to hit that same data record. That's where you then have to kind of get creative and say, well, how do we replicate this data, even if, maybe we're going to have a little bit of loss of accuracy there, saying I'm going to have, 6 copies of this spread around, and I'm going to, sync them up, every 100 milliseconds or so, but I'm going to let them drift a little bit from each other, just so that we're not constantly having everybody trying to lock on the same item. So, that, as I say, in that particular billion operations benchmark, I don't think we ran into problems of that sort. But in real world use cases, I would say, hotkeys is kind of, one of the big ones.
Have you ever tried to hook a rules engine to your environment to, instead of using AI on it, instead of using something like that to actually govern the types of decisions, a rules engine to actually enhance what the data is doing and giving like a decision model back?
And I'm not an expert in that area, but I still thought myself, qualified to go and write a little dumb implementation of a rules engine. So it's actually something that I did as one of the first demos that I built when I joined the company, is to go through and do like a little simple rules engine. So I mean, it's definitely something that you can do, because as I say, I kind of implemented one that, and I did it specifically because at the time, one of the things we made all of our new engineers do is go through this coding exercise related to fraud detection. And so I thought, well, I'm going to take that certification exam that I had to go through and do when I started, and I'm going to do some additional work on trying to build a rules engine around this that did take advantage of exactly those things. It's like, well, I can just have rules and rule sets and evaluate all the rules within a rule set and come up with some sort of score, and then have some way of aggregating all those scores and giving them weights. And again, it wasn't a very sophisticated implementation because I didn't have a tremendous amount of time to spend on it. But I thought conceptually it said, hey, this is really a viable approach to use with Hazelcast, is to run, to run through that sort of a rules engine architecture. And I think it's just actually kind of a matter of the market right now seems to be enamored of machine learning solutions, and that's what people want to see. So since we don't build those ourselves, we kind of went out and started building integrations that show, oh, here's working with H2O AI, or working with now I'm drawing blanks on some of the names, but we did like 3 or 4 of these sample integrations just showing like scikit-learn was one of them, and TensorFlow was one of them. So we've got several examples of this, but we're really just kind of the execution engine, if you will, and what we're executing, whether that's an AI model, a rules engine, or just like a bunch of Java code, is kind of, pick whichever way you want to do it.
Well, no, it's nice that, but you alluded to sort of like the ideas of a rules engine when you were talking about fraud detection within your banking experience of someone buying something on where their phone was not at. And I had experience with this with another credit card company, and they really ran 200 rules for every transaction, especially if the client really wanted the advice back. In other words, it was always given as a solid service, but if they really wanted to wait for it, by God, they wanted that advice back if they started to actually, example, purchase something over $10,000.
Yes. So I heard what you were saying. Was there a specific question there? Because I'm
no. You kind of like answered it, but it's almost like it's got to be proof of the pudding, because I liked your large transaction rate per second that you're giving. If you have something like as a deck that you could send out, or something that you could publish about it, because I'd be interested in seeing how the architecture was to accomplish that, to how you put it on AWS and actually ran it, because we were running something like, I think we had 4 CPUs per server. I think each CPU had 4 cores. And we were running something like 80,000 transactions per second per compute. So I think, it ramped up to where you were at, but I'd be interested in seeing how it was architected on AWS.
Yeah, let me, I'll post a link in the chat. Because as I say, I didn't have the.
Yeah, I just got it. Thank you. Well, I'm very interested in this. Thank you.
Sure. And again, I'm not sure if that has all the detail you're looking for in that, but if not, feel free to reach out to me afterwards, because I think, I could be wrong about this, but I think the code that was used for that is on GitHub. So I think it's all, publicly, you could run it yourself if you were so inclined. And if not, we could probably still make it available, because like I say, it is a standard benchmark
Thank you.
Mike, I think you do have a question sitting there in chat from VJ.
Yeah, and I think the answer is yes to both. I know that it's true for S3 because I saw that on one of our slides. I think there's a connector for Hdfs as well. I think this there's a file system connector that yeah, here we go. Hdfs, S3. So yes, I think we can deal with all of those as either sources or sinks. Google Cloud storage as well. I think we try to be agnostic across cloud providers. So if we, have an Amazon flavor of something, it's likely we have an Azure and GCP flavor of it as well.
Okay, any more questions here for Mike before we move to the raffle? Okay, well, hearing none, thank you very much, Mike, for a great presentation.
Well,
I'm
thank you
going
for having me.
Sure, glad to have you. And when you get the slides to me, I'll see about getting them posted here. I'll send them on after that.